you all the people who are attending from around the world, or certainly in Europe. Thank you very much for coming online. I'm sorry it's been delayed, but as you probably appreciate, a number of things are a bit different today. One is that Luca is unable to be here, and so it's taken a while to set the technology up. But here we are, and I hope you're ready for two talks, which will take roughly 90 minutes each, with a 30-minute break between. And I will now introduce our speakers and the title of their talks, and then I will invite the first speaker to start. Okay, so everybody, the title of the two talks, one is from Shane Hattingh, the Technical Director of Gaffney Cline. He's going to talk to us today on carbon capture and storage, quantifying geological storage. And then after our break, Drew Powell, who's the Projects and Energy Transitions Director from Gaffney Cline, will talk to us on carbon capture and storage, project development, equipment facilities, aspects and project commercial considerations. So we have a very comprehensive program today on carbon capture and storage. So just a short introduction to Shane's talk to start with. So Shane's presentation begins with a brief introduction to CCS and why we need it, followed by discussion on the phase behavior and physical characteristics of CO2. Saline aquifers and depleted gas reservoirs as storage sites are treated in two sections, and the focus is on estimating storable quantities. Topics include trapping and immobilization, quantitative analysis, material balance, dynamic modeling, workflows, and examples drawn from experience. Now, Shane is a reservoir engineer with 36 years working experience and currently holds the position of Technical Director at Gaffney Cline. He has worked on CCS evaluations, peer reviews, and integrated studies on some 15 projects worldwide. His experience includes screening, ranking, and selecting CCS sites, region-wide evaluations of CCS potential, and estimating storable quantities, risks, and uncertainties in saline active aquifers and depleted gas reservoirs. Shane, the floor is yours.
Thank you, John. Do you need to say anything about questions?
Yes, questions. Actually, Luca, can you explain the way we have questions, and I'm going to answer them?
Yes. So to everyone who's following the event from YouTube, below the video, you can find a link to a question form. By clicking on the link, you will be redirected to a Google form to compile with your name, surname, and question to ask, and obviously specifying to which speaker address the question. In this way, team will receive your questions and will be able to ask it to the reference speaker. So just take a look in the description of the video below the video you're seeing now, and feel free to ask as many questions as you want.
Thank you. Well, good afternoon, everyone, and welcome to this talk. Welcome to everybody in this room. It's wonderful to see so many faces from years gone by, and welcome to everybody who is dialed in remotely. Before we go any further, I do need to point out that the material and views expressed in this presentation are my own. The material has been prepared responsibly and carefully, but please understand that no warranty expressed or implied is given that the information is complete or accurate, nor that it is fit for a particular purpose. So what is geological storage of carbon dioxide? At a broader level, carbon capture and storage is the process of capturing and storing carbon dioxide before it is emitted into the atmosphere. And more specifically, the geological storage is the placement of carbon dioxide in deep geological formations where we anticipate that it will remain safely isolated from the atmosphere for forevermore. There are three principles of geological storage. First of all, quantity. How much can we store? Injectivity. How easily can we inject the carbon dioxide into formation? And containment. How safely can it be stored? So this presentation this evening focuses on the estimation of storable quantities in saline aquifers and depleted gas reservoirs, and that's illustrated on the diagram on the left-hand side. Also in that diagram, you'll see use of carbon dioxide in enhanced oil recovery. We won't be talking about enhanced oil recovery tonight. So as Tim has said in the introduction, we've had the privilege of working on quite a large number of projects worldwide, and we've seen how different people do things differently, and we've gathered a fair amount of experience and knowledge from that. And the purpose of this presentation today is to share that information with you. It is true that the evaluation of CCS sites is still in its infancy, and we're all trying to learn how it works. And there will be people in this room and on the call who will have different experiences from our own and who may differ in views from our own. And I hope that during the question and answer session, we can explore some of those differences. I'd like to start with a discussion on the physical properties of carbon dioxide because it is an unusual gas, and it's really important when we do our estimates of storable quantities. We treat storage in aquifers and depleted gas reservoirs differently because they are so vastly different in so many respects. And then I'll conclude with a summary where we compare depleted reservoirs with aquifers and then open the floor for discussion. So let's move directly onto the physical properties of carbon dioxide. I'm sure that most people in this room will be aware of the phase diagram of carbon dioxide, which is the diagram on the left-hand side. The vertical axis is pressure, the horizontal axis is temperature, and it shows the three main phases, gas, liquid, and solid, where the domains lie on the phase diagram. There's a triple point where gas, liquid, and solid are in equilibrium. And what's more important to us in CCS is really what we call the critical point. And that occurs at a temperature of 88 degrees Fahrenheit and just over 1,000 pounds per square inch. And above the critical point, the fluid is a dense phase supercritical fluid. So what does that mean? We're going to focus now on the density of carbon dioxide, because that tells us an awful lot, and we use density throughout our calculations. So the diagram here is density in tons per cubic meter on the vertical axis plotted against the pressure. And each one of those lines is a different constant temperature. And the temperature is cool at the top and it gets hotter as you go down. So the blue line at the top is the coolest, and the blue line at the bottom is the warmest. The grey line, the grey vertical line, is the critical pressure, just over 1,000 psi, and that red line that you see is the critical temperature of 88 degrees, and so the red dot is the critical point. And if I can point it here, this is the area where we have the supercritical fluid, and that is where we try and do our CCS. So a few important points. Density increases very sharply with pressure above the critical point, but is less sensitive to pressure at higher pressures. The density decreases with increasing temperature, and it is sensitive to temperature over a very wide range of pressures. And the density of carbon dioxide is very important because it tells you how much what the concentration of carbon dioxide is in the pore volume. So it tells you how much you can fit into a given pore volume. And in a nutshell, the higher the density, the more molecules we can fit into any given pore space. But what happens when we go below the surface? So this is a similar diagram to the previous one, and there are 2 points. First of all, when we go down, the pressure increases, and therefore the carbon dioxide becomes more dense. At the same time, the temperature increases, and that tends to make the carbon dioxide become less dense. So the temperature and the pressure effects act against each other. And what I put on here, this black line, is the relationship between density, pressure, and temperature for a typical temperature gradient below the surface. And if you look at that, you'll see that it increases very rapidly, but then it eventually becomes flat, and the temperature and pressure effects more or less cancel each other out. And so in general, there's no real benefit to going deeper and deeper and deeper, because you don't put any more carbon dioxide into your pore space. One really important point is that the temperature is not always a normal gradient, and it can vary a great deal. And we'll see some examples of that later on. And so you can get a lot of scatter all over this area, where you have different in different environments. Okay, so very small variations in temperature can have a big impact on carbon dioxide. So with an understanding of the density, we can easily convert from volume to mass. We can, with density as a starting point, we can calculate the gas expansion factor, and that is of carbon dioxide. And that is the density of the carbon dioxide in the reservoir divided by the density at surface. So that gives you a gas expansion factor. And we'll see that time and time again. A point to note is that carbon dioxide can have a very high gas expansion factor. And it's not unusual in a depleted gas reservoir to discover that you can fit more carbon dioxide expressed in surface conditions, volumetric conditions, than the volume of hydrocarbon gases that you took out of the reservoir. And that's because of the ratios of the gas expansion factors. I'll see more of that as well in examples. And just a further note on the gas expansion factors, this illustrates the point. You've got, we've taken carbon dioxide and methane, and what you see on this diagram is the ratio of the gas expansion factor of carbon dioxide over that of methane, with depth below the surface. And as you go, you can see as you go through the critical point here, that ratio can get very high, more than 3 times. Eventually, it starts to come down again as the temperature effect has temperature effect is greater on the carbon dioxide than on the methane gas. But generally, you'll always get more carbon dioxide than gas. These results are affected by actual composition of the hydrocarbon gas, any contamination in the injectant, and any anomalous temperature gradients. Okay, so that's the properties of carbon dioxide. Let's move on to CO2 storage in aquifers. And the first 2 slides are a background. Many of you will be familiar with this. We need to look at what the mechanisms are in aquifers to contain the carbon dioxide. And the first of those is geological trapping. So that is where the carbon dioxide gets injected into a geological trap, and it gets stored in a similar fashion to what hydrocarbons might get stored in reservoirs. And that's illustrated in the 2 little diagrams. So in geological trapping, you can get a very high concentration of carbon dioxide in your trap. But carbon dioxide is always then stored as the free phase. It's not immobilized, it's stored there. And of course, there always is the risk of seal failure. The second type of mechanism is residual trapping. And that occurs when the carbon dioxide migrates into the aquifer and disperses over large distances, displacing the brine ahead of it. The brine then imbibes into the carbon dioxide and traps the carbon dioxide molecules as it moves into the plume of carbon dioxide. And of course, what's important here is the critical gas saturation in your simulation. And the more contact that carbon dioxide has with the rock itself, the better. So sometimes heterogeneities are helpful. This is a very important form of immobilization of carbon dioxide. The next is solubility trapping. So carbon dioxide, when it's injected, it progressively dissolves in the brine and it becomes immobilized. The more contact you have with the water in your reservoir, the better. The diagram on the right-hand side shows solubility of pure carbon dioxide in fresh water. And in the typical temperature pressure ranges of CCS sites, it might be anything between 3 and 5%. It's affected by salinity. It works better at low salinity, works better at high pressure, and it works best at low temperature. In addition to the carbon dioxide dissolving in the water, once it has dissolved, the water becomes more dense and it would tend to want to sink. And there is a theory that convective currents could be established, and that would allow water from deeper down in your aquifer to move up into the plume of carbon dioxide and mix with the carbon dioxide, and so you get a continued long-term immobilization of the CO2 in an aquifer. Solubility trapping is a second equally important form of immobilization. Finally, there's mineral trapping, and that's when CO2 dissolves in brine. It alters the chemistry. It dissolves some of the minerals and precipitates other minerals. That is considered a very, very slow process, but it is very, very secure. In most calculations that we do today, we don't bother with mineral trapping. It's a long-term chemical effect. So the most important two methods that we will be looking at are solubility and residual trapping. This is a very helpful diagram. It comes from a publication by Ringrose, and there are many such diagrams floating around. And it shows on the horizontal axis time, and on the vertical axis the fraction of the carbon dioxide that's being injected and how that carbon dioxide has become immobilized. And the mechanisms for immobilizing CO2 change over time. So initially, the CO2 is mobile. Then we have residual trapping and dissolution of the CO2 in the water. And as time goes on, we may get mineral phases forming, and we may have secondary migration of secondary units occurring. But it is true that in any assessment of an aquifer, one of the most challenging things is to understand what happens to the this free phase of CO2, because as long as the CO2 is not immobilized or contained within a trap, it can move, and it would move. And so there's a lot of study going on to try and work out what happens to your carbon dioxide in the long term. And to do that, you really do need very good dynamic simulation models, and you need to run sensitivities and test alternative scenarios. So in estimating the storable quantities of CO2 in aquifers, you'll often see this volumetric equation that's shown here. The mass of carbon dioxide that can be stored is equal to pore volume times some efficiency factor multiplied by the density of the carbon dioxide. And to estimate efficiency factors, there are two equally important considerations. First of all, the mechanism for trapping and immobilizing the CO2 must be known, and the nature of the container must be understood. And we'll show that on the next slide. So here we have 4 possible combinations. On the left-hand side, we have open aquifers, so aquifers that are infinite acting. And on the right-hand side, we've got 2 confined aquifers. So that is where they've got a limited volume. And then on the upper two diagrams deal with geological stored trapping, and the lower two diagrams deal with solubility and residual trapping. So let's just have a look at efficiency factors, and we'll start with the upper right-hand corner where we have a confined aquifer, and it is in a geological trap. And there the efficiency factor is simply the total compressibility of the system multiplied by the pressure that we can increase it by. And you'd expect that to be small, and efficiency factors of maybe 0.5% are considered. It increases with dissolution. It increases with depth, because the deeper you go, the greater the value of the delta P is that you can tolerate. And of course, it increases if you can extract the brine. So by brine extraction and pressure management, you can increase that. But generally, they're considered quite small. We move over to the other side, where we have an open aquifer and a geological trap. the efficiency factor is, the maximum efficiency factor is simply 1 minus the irreducible water saturation. That never happens, but you would expect, typically we see in the literature, and people expect to get about 30 to 40% efficiency factor when applied to the pore volume of the structural closure itself. The more difficult cases are these at the bottom here, where you're relying on solubility and residual trapping and the migration of the plume of carbon dioxide into either an infinite aquifer or an aquifer which is contained. And there's no direct calculation that you can do to estimate that. And if you look in the literature, you'll see over and over again a range of efficiency factors between 0.5% and 7%, and in some cases considerably higher than that. The problem here is how you define the container, and that is determined by your development plan. Just say a few more words about the efficiency factor in these open aquifers. This is a diagram that from a publication by Ringrose again, and they've estimated efficiency factor using as an independent variable the gravity and viscous ratio. And why is that the case? So if you look at the injection here on the right hand side, when we inject into the formation, the viscous forces in the well force the carbon dioxide laterally away from the well, and that gives a lot of contact with the rock and with the water. But at the same time, the gravity forces tend to make the carbon dioxide float up and run along the roof of your aquifer, and that kind of removes it from accessing the aquifer here, the water here for dissolution. And so gravity forces are bad, and the viscous forces are good. And so the ratio of gravity to viscous forces is a indication of the efficiency factors that you might be able to achieve. So obviously something like this, where you have lots and lots of layers, and the migration of CO2 into the different layers can increase the efficiency factor quite significantly. But the point of all this is that the efficiency factors that we've looked at of 0.5 to 7% do have some grounding in the theory. Just one warning about using efficiency factors. This is a extract from the SPE, carbon dioxide storage resource management system, the SRMS, and they offer this definition for storage efficiency. And if you read that, you'll see there are 6 different interpretations of what storage efficiency can be. And unless you know what storage efficiency people are actually using, it's a pretty meaningless number. Okay, so I'm going to go on to look at 2 worked examples now. The one is a regional evaluation in the Middle East, and that deals with efficiency factors, and the other one is a case study in the UAE. So this is a piece of work that was done by ourselves. It was for the Oil and Gas Climate Initiative. We did that with AFRI. And we were tasked with estimating the potential for storing carbon dioxide in the GCC countries in the Middle East. And we did aquifers as well as depleted gas reservoirs. So just a quick look at the geology here. The diagram, that's a geological map of the Arabian plate. On the left-hand side here, we've got a basement outcrop, and here we've got the sedimentary basin, which dips down towards the east. Most of the formations outcrop here against the basement high, and this is where the prolific oil and gas developments are. So we looked at the both at the basin, and then we also looked at the ophiolites, but we won't be talking about that 2 in 1. So first thing to do was to go and identify. So this is very much exploration type work. First thing to do is identify what possible aquifers could be used for CCS, and we did that by trying to match up aquifers and seals. So go through the formations and find where you've got a good seal and then look for an aquifer below. Seals come first, aquifers come second. And we've listed those there, about 11 of them in total. And I'll say a bit about the first one just as an example. So this is the UER storage play. And the diagram that you see over here it's all based on public domain information. We didn't have anything else besides that. But the first thing we looked at is what is the depth of the formation, because we need to be within the critical domain. And the second thing we looked at is what is the salinity of the water, because many of these formations, as the further you go inland, the water gets used, and so there's a limit to where you want to put in any CO2. In the formation, in the east itself, the salinity goes up to 170,000 ppm, so that's fine. So we had a cutoff here of salinity, and we had contours of depth, and we did this for each of the different formations, and then we stacked them all up, and we color coded them where we felt there was overlap between them and where the potential was. So you see in the UAE, there's a lot of up to 6 different aquifers available, but they're also up here and up here. And that's quite convenient because this is where all the CO2 emissions take place in the Middle East. And once we had done that, it was a simple matter of estimating the storage capacity by taking a view on the area of the fairway, the thickness of the reservoir, net gross porosity, carbon dioxide density, and the storage efficiency. And for that, we considered a range of between 1 and 6. We did a Monte Carlo calculation, and we came up with those volumes, those quantities at the bottom. So low estimate of 40, best estimate of 119, and a high estimate of 317 gigatons. So a very wide range of uncertainty, as you would expect. But just to get things in perspective, 40 gigatons is about what we emit annually in the world. So at the low case, you would be able to store 1 year's CO2 emissions. The next example is another study in the UAE. This is from a paper by JE. It's not work that we've done, but I'm putting it in here because it does provide a very pragmatic approach to dynamic simulation and running the models and a good workflow. They looked at several formations as we did, and these are common to the previous study. They looked at 4. This is the setting. So on the right-hand side here, that's the region that was looked at. And if you look in more detail over here, you'll see that you've got a syncline over here with surrounded by oil and gas fields around it. And of course, that does pose questions about the suitability of anything here, because carbon dioxide will tend to migrate up, and there's a risk that it reaches the producing oil fields. These are the properties of the 4 formations that were used, and I've outlined in green where we have a good properties, and red where we have very poor properties. This is the UER formation that we looked at previously. So this formation, the Schreiber, has very low porosity and permeability. However, the study was done using the Schreiber because it is the deepest, and it has the least chance of affecting the producing oil and gas fields. But what was really good about the study is the way that it was approached in terms of these simulation. They used CMG's GEM software, and then there are 5 priorities. And the first thing to establish in any dynamic modeling of an aquifer is where's the plume going to go? And they did that by running simulations with 2 immiscible phases. That's just to find out where the plume is likely to go and how it will disperse. They then went on to include solubility in that so that they could assess its component. They then went back to step 1 and included the residual trapping in it. And then they combined all the processes. And that was, it's a very pragmatic approach, and it is very systematic. So by running the sensitivities with different components individually, you get an idea of what the contribution is, and running them all together, you can see how they interact. This is the main result over here. I mean, the results are not that easy to extract from the paper, and so the diagram on the right-hand side here is what I've managed to extract, and I hope it's correct. But it shows that after 100 years of injection, there's a huge amount of free-phase carbon dioxide still present. There's a fair amount of carbon dioxide in dissolved in the water, and some residual. And as time goes on, you'll see the free phase gets less and less and less, and the other two components become more and more important. But even after 4,000 years, it shows here that there's still a lot of free phase carbon dioxide in the rock. There were various analytical calculations done with ranges of efficiency factors, which are shown over there. And I just wish to point out that for the Schreiber itself, the simulation showed 960 megatons, which corresponds to an efficiency factor of about 2% in this case. Okay, so that's everything I have to say on the aquifers, and we'll move on to the depleted gas reservoirs now. So this little diagram shows the evolution of a gas reservoir from its initial state through depletion to a low pressure state where it would normally be abandoned. It then gets converted to gas storage, and we repressure it up with CO2 back to the initial pressure. And that's generally what people try to do with depleted gas reservoirs. So there are different ways of estimating the volumes that could be stored there. And you could do it through complete conventional geoscience estimation of whole volume, or you can use material balance. And since we know how much has been taken out of the reservoir, we should be able to calculate how much is going to go back in. And that's a material balance approach. So this is a derivation of the material balance calculation. And I think in the interest of time, we probably won't go through all this. But it will lead to a formula which I'll show in the next slide. If essentially we start with initial pressure up there, it gets depleted, we restore the pressure up to some storage pressure with carbon dioxide, and we want to know how much we can store in there. If you were to work through this, each of these has got a separate step with an equation. If we put all that together, then we get this big equation at the top here, which is general material balance equation for the for storage of CO2 at any pressure. If we pressure up the reservoir to the initial pressure, then that equation collapses into this very simple little equation down here, and that's really useful because you can do it to the back of an envelope. So what it says effectively is that the mass of carbon dioxide that you can store is equal to the volume of gas that you've produced divided by the gas expansion factor of the gas at initial conditions multiplied by the density of the carbon dioxide. So really all you need to know is the produced gas volume, something about its PVT, and the temperature and pressure to calculate the density of the carbon dioxide. And that will give you a first pass estimate of the quantity of CO2 that you can store. So this is a simple material balance calculation, and what it does, it has its limitations. There are many factors that will result in different results coming out. Several factors that will cause the volumes to be less, to decrease, such as aquifer influx and heterogeneity. And in what we've seen, aquifer influx and heterogeneity are the two factors that have the biggest impact on your estimates of CO2 in depleted gas reservoirs. Condensate dropout can be quite large. Impurities in the injectant can be significant as well, and hysteresis and full volume compressibility, which is expected to be quite small. There's certain things that will allow the volumes to increase. So if you could utilize the aquifer surrounding the pool, that's potentially large, and of course dissolution in cholated water, which is usually quite small. The other effects, like thermal effects, mixing with the remaining hydrocarbon gases, and vaporization of the cholated water. So in the next few slides, I would like to take you through a worked example. And this is a field, a gas field with bounded by faults. It's a dry gas pool, and it has a small aquifer, good quality sandstone. We have all the parameters, reservoir parameters, and we can calculate the gas in place of 477 BCF. It's a temperature of 160 degrees Fahrenheit and 2000 PSI. That's the starting point. Field then produces, and it recovers 344 BCF after 14 years. There's a recovery factor of 72%, and abandonment pressure is 604 PSI. And then it gets converted to gas storage. So first thing is that we need to understand the PVT of the hydrocarbon gas and the carbon dioxide. From our laboratory reports, we've got a Z factor as a function of pressure. And from temperature and initial pressure, we can calculate the gas expansion factor of the hydrocarbon gas at 132. And likewise, we can, for the carbon dioxide, we calculate what the densities are, and we get a gas expansion factor for the carbon dioxide, 236 at the initial condition. And then we can simply put it into that little equation. Everything else is a known, and we end up with an estimate of the storable quantity of carbon dioxide at 32.5 megatons. Now that's 613 BCF. And so you produce 344 BCF of hydrocarbon gas, and you can theoretically store a maximum of 613 BCF of carbon dioxide in there. We can expand that equation to use the big equation, and that gives us the storable quantities at any pressure, and that's simply plotted here. So we start at the abandonment pressure at 604. We increase the pressure. This tells us how much CO2 we can store. We go all the way up to initial. We get the 32.5 megatons. So the assumptions in all of this is that the carbon dioxide is pure. There are no contaminants. There's no mixing with the hydrocarbon gas in the reservoir. And this gives you the theoretical maximum. So if you inject CO2 into a depleted gas reservoir, what does it want to do? Well, this shows the density of the carbon dioxide and the density of the gas as the pressure increases. This is the density of the hydrocarbon gas, which gets compressed. And this is the density of the CO2 as it gets compressed into the reservoir. CO2 is always more dense than the hydrocarbon gas. So when you inject it into the reservoir, it doesn't float to the top as it does in an aquifer. It sinks down and it accumulates at the gas water interface or the gas oil interface. But what happens if the gas does mix with the hydrocarbon, if the CO2 does mix with the hydrocarbon gases? So generally what is likely to happen is that you reduce the quantity of CO2 that you can store if there is a complete mixing with the residual hydrocarbon gases there. And to illustrate the point, we've taken carbon dioxide and methane, and we've looked at mixing them in ratios from pure carbon dioxide to pure methane. And then we take a quantity of the mixture, and we can work out, if we take that down to reservoir conditions and they were separated, what volume would they occupy, compared with if we take it down as a mixture, what volume they would occupy. And you take the difference between the two, and that is shown here as a percentage of the state where there's no mixing. So as the bulk percent of the methane increases, so the volume that you require downhole to accommodate that mixture increases, reaches in this case around about almost 10%. So there can be quite a significant loss in your storage capacity if the carbon dioxide mixes with the gases in the reservoir, as opposed to if they remain segregated. And that's dependent on the temperature and the pressure. So this is a kind of a low temperature and pressure scenario, and this is a higher temperature and pressure scenario. As the temperature and pressure gets higher, so the effect gets less and less and less. I've seen calculations done that show even more dramatic losses in CO2 storage than the 10%. That can be very significant. So why is that happening? Well, it's happening because of the Z factors of the mixture. So this dashed line here is the molar weighted Z factor of the mixture, whereas this solid line over here is the Z factor of the mixture. And the Z factor of the mixture is greater than the weighted average Z factor. Therefore, the expansion factor of the mixture is less, and you get less gas down in the storage space. So if we relate this to the previous example that we just showed, we calculated that you could lose about 8% of your carbon dioxide storage capacity if it mixes fully with the residual hydrocarbon gas. So how are we doing for time?
You carry on as you like. Don't worry about the time.
Okay, all right. The second thing we want to talk about is if there's contamination of the injectant. So everything we've looked at so far has been pure carbon dioxide, and this is an example of where carbon dioxide has got some nitrogen mixed with it. And the diagram that you see here, it shows a quantity of carbon dioxide that can be stored in a given pore space downhole when nitrogen is present in the injected stream, and it's expressed as a ratio of the quantity of pure carbon dioxide that you would be able to store. So with pure carbon dioxide, it's 1, and as the injectant, as the nitrogen content increases, so the amount of carbon dioxide that you can store obviously decreases. And there are two parts to this. So one is the physical space that the nitrogen takes up when you put it down the hole. And the second thing is the change in the Z factor and the gas expansion factor when the nitrogen and the carbon dioxide mix with each other. And what you'll notice here is the gas expansion factor, in this case for carbon dioxide, is 348 surface volume per reservoir volume, whereas for nitrogen is 124. So nitrogen takes up a lot more space downhole than carbon dioxide does. And because of that, 5% contamination in your well stream with nitrogen leads to a loss of more than 10% of the storage space for the carbon dioxide. On top of that, you get the mixing and the Z factor effect. And so you, in this case, 5% nitrogen results in about 18% loss of your storage space of carbon dioxide. So it's really important to be aware of when you're injecting carbon dioxide that it's often not pure, and that relatively small impurities in it can have an impact on the volumes, more than what you'd expect simply from the molar concentration. Okay, so I'm going to go on to a few case studies now.
Can you pass me that other microphone now? I'll just make sure that people can use it if they need to ask questions.
Yeah. So once again, I've got a dynamic modeling workflow for depleted gas reservoirs, and I think we're going to not go through all this because it will take up more time than what we have. But I'm going to go through 3 examples. These are examples based on real studies. They've been drawn from real studies. This is an example in Europe. We have a very good quality reservoir. that has it's fault bounded, got a tiny aquifer, high porosity, high permeability. It's a dry gas. There's no condensate dropout. It behaved like a tank. Here the Z plot is smooth and it's very well behaved. The 3 producers are being converted into 3 injectors, so it's the same wells that are being used twice. It's a fairly deep reservoir. Initial pressure was above hydrostatic, but the temperature is normal. We get quite a high CO2 density of 0.65 tons per cubic meter. Depletion pressure was extremely low, about 400 psi. And so the material balance calculation gives us 39 megatons. It's not huge, but it's substantial. The dynamic modeling shows 36.1 megatons, so it's a loss of 7%. So, here we have a case where you do your calculations, you do your material balance, then you run your simulator and you get less out. And so, the questions of why. Well, there's a tiny amount of water influx, which is not accounted for in the material balance. There is mixing with the remaining gas in there, so that's a loss, but it's a very high temperature and pressure, so the loss is not that big. There's a tiny hysteresis effect. This is a very good candidate for carbon dioxide storage. So that's a good one. The next one is in another part of the world. It's also a good quality reservoir. It was also a dry gas, was developed with quite a large number of production wells. And the plan is to use only 3 carbon dioxide injection wells. So the issue with this reservoir is that it is made up of many layers of shale and sand, and therein lies the problem. So it's capturing the P over Z plot, so the pressure is not depleting equally throughout the whole reservoir. Certainly differential depletion was seen in some of the wireline pressures, and so there's some concern about the communication across the reservoir. And so the initial simulation model that was used for this was fit for purpose for predicting the depletion and managing the depletion of the reservoir. It was used for estimating the storable quantities. The material balance calculation showed 17.4 megatons, and the simulation showed 14.8 megatons. That's a loss of 15%, which seems quite small. But the big thing is that there's a great deal of uncertainty in it, because you just don't know how well you'll be able to access all that pore space by injecting into only three wells when the field itself depleted using a great many more wells. And so this is a case where sensitivities need to be run, the simulator needs to be, different realizations need to be considered. And we ran the different sensitivities, and we got a much wider range of uncertainty in the storable quantities in this reservoir because of the risk of communication being poor. So losses as high as -35%, -15% and -5%. And this illustrates a point that the dynamic model that has been history matched for depletion and might be fit for purpose for depletion is not necessarily going to give you the correct forecast when you turn it around and you start injecting carbon dioxide. And we know that from analyzing conventional gas storage facilities. So, and then the final little example is one of a gas accumulation with oil rim, very complex structure with many compartments. The oil rim was developed with horizontal wells, and the plan is now to turn it into CO2 injection with also quite a large number of wells. But during production, the water encroached into the oil encroached into the gas, and then the gas was blown down. Dynamic modeling was done. It was quite a good history match. That was converted into a compositional model for CCS. It's a very shallow reservoir close to surface. The initial pressure is slightly above hydrostatic, normal temperature, and you can see the CO2 density is quite low, 0.26. The material balance calculation showed 12 megatons, but the simulation 8.4, so it's a loss of 30% of storage. And that is due to aquifer influx. It's due to the complex geology and uneven repressuring up of the reservoir. It's due to complex fluids. The reservoir is also very shallow, so you don't have much scope for increasing the bottom hole injection pressure. And we felt that the storable quantities could even be lower than those that we estimated there. And this is certainly not an optimal site for carbon dioxide storage. Okay, so I have one more example that I want to show. And this goes back to the OGCI study. You previously saw the aquifer work that we've done. We were also tasked with calculating or estimating the storable quantities in all of the gas reservoirs in the whole of the region, which is quite a big task. It's all based on public domain information. So the first step was to go and try to work out how much non-associated gas has been produced in the past and how much non-associated gas will be produced in the future. There are several publications and of the volumes. We collated all of that information and made estimates of the ranges of uncertainty in the total volumes of gas that could be recovered ultimately from each of the countries that we're looking at over here. So these are the estimates. This is all published information in the OGCI report. And that was all we had. That's the only information that we had to go on. And so we had to be a bit innovative here. And I see that the formula, the critical formula, is missing from the top here. But never mind. We used the first thing was once we've got the volumes of hydrocarbon gas that have been which would be likely to be recovered, we had to convert that into CO2 storage. And there are four factors that came into play. These are still shown over here. So first of all, there's a utilization, the ultimate recovery of the hydrocarbon gas, which we've got. There's a suitability factor. We know that not every reservoir is suitable for CO2 storage. And so we took a guess on what fraction of the reservoirs might be suitable for CO2 storage. And those are shown, suitability factors are shown there. We used an efficiency factor over there, but then the difficulty was converting those volumes of hydrocarbon gas to carbon dioxide. And of course, we don't know what the gas expansion factors are. And so we used an uplift factor over there, which comes from this type of analysis over here, 1.2, 1.4, 1.6. Anyway, that was all put together, and we did the calculations, and we came up with a range of potential storable quantities, 15, 41, and 90 gigatons to be stored in those reservoirs if they all eventually became depleted. So,
excuse me, Shane, can I just clarify? You previously showed figures for Saudi of 40, 119, 317. Did I misunderstand that? That wasn't storage.
So these are in depleted gas reservoirs. These are in gas reservoirs, and the previous one was for the aquifer. Yeah, okay. So they're two different.
It's best if you, unless you have a good loud voice, then use this, because otherwise people won't hear on the Jabra. Luca, can you hear my voice easy enough on the Jabra? He's not there. Well,
yes.
Okay, thanks. I'm really glad you put this up, because I was going to say, in summary, it looked to me like, if you're lucky, the amount of gas in a reservoir could be replaced by about the same amount of CO2, if you're lucky, because the density factor means that you should be able to put more in if you go up to the maximum initial pressure, but all the negative factors of inefficiencies everywhere else claw you back again. So I was saying gas for gas, 1 to 1. Is that about right?
I'd be reluctant to make a general comment on that. I mean, we do have cases where we're highly confident that we will put more carbon dioxide than hydrocarbon gas in, and that can be 1.5, 1.6 times. But the others we were less confident. So I wouldn't say 1-to-1 necessarily. I mean, in this case,
It's rather less than 1-to-1.
in this case, it's less than 1-to-1 because we've got 1,000 TCF there, and we've got 784 TCF.
So it's like 60%.
And that was a lot less. And the reason for that is because this is more like it's more like an exploration type thing where you've almost got a risk factor here. You've got your suitability factor of 0.5. So we cut everything in half to start off with.
Well, and the 40 gigatons, just do pitch in so long as your voice is loud enough, otherwise you can use this microphone. But the 40 gigatons, you said, was only 1 year of
global emissions.
So all these Middle East countries, all their depleted reservoirs, if this worked out, would still only store 1 year's CO2.
Yes, that's where we stand at the moment. Yeah.
And then the previous one on the Ceylon aquifers was the best case. No, the worst case was 1 year. Yeah. The top case was 7 years.
Yeah, something like that.
So this isn't doing it for us globally.
No.
Right. Okay. Please do pitch in. I've got one more. I've got one question.
Kim, obviously, that's only one area.
Yeah, but this is the flipping Middle East.
Yeah, no, I realize that.
And this is only this. What about with methane, which is roughly what the gas reservoirs are? That's where you get the one molecule of methane gives you 1 of CO2. You start looking at the crude oil, then you're going to have 1 molecule of crude oil producing 15 or 20 of CO2. So this is the very, very best case.
Yeah, but I think I'm sure Shane will agree that CO2 storage is only on a sort of a local basis. So Middle East probably is contributing 10% of global CO2, I'm guessing. So this is if you want to store what you produce locally, this is perfectly fine. But of course, Middle East is not expected to store the entire global CO2.
But we haven't talked about the crude oil. This is just the natural gas, which is your best possible case. Am I right there?
Yes, absolutely. I would say that these estimates, these quantities are quite reasonable in comparison to the emissions in the Middle East, because that's where the CO2 will come from. So I don't have the figures here. The report does have those figures, but then we're talking about many years of the local emissions could be disposed of through this process.
What about the cost of injecting the CO2? The cost, I mean, how expensive it is to inject all this amount of gas in these depleted reservoirs.
Yeah, so that is a key question, and it's the thing that the incentives that are being put in place in different parts of the world are making it more attractive for people to do this. Without the incentives, it becomes very difficult to do. And incentives can be positive or negative. So if you don't do it, you get taxed. And those incentives are giving carbon dioxide a higher and higher value all the time. I don't know, Drew might be, Drew's nodding. He's going to be talking about that in the next talk.
I was thinking of Rami's question when he said the Middle East only produces less than 10% of the world's global gas emissions. So presumably it pays for the Middle Eastern countries to import CO2 from other countries and store them and make money.
I think we're getting into Drew's talk here.
Behind you.
Yes, I mean, Drew's going to give, you're going to discuss more of some of these things. Yeah.
You're going to answer the question?
We'll cover it and see if it answers the question.
Well, I haven't heard about CO2 tankers.
Yeah, you've got to move it to the Middle East, haven't you?
Yes.
Your question. Come on.
Yes, mine was a little bit more on the operations and just grabbing your brain. So we have seen how important is the CO2 density to the storage capacity, right? In terms of operations, how feasible is actually to inject CO2 in super critical conditions? And this is actually what we all want. And when you do the simulations, everybody's like, no, we want to inject it in super critical conditions because we want that to be dense, and it's the best, and this is, how we want to be. But how feasible is that? Based on your experience, right?
So you also
inject the CO2, and how do you guarantee, right? Because in the future you're going to have utility problems, et cetera. So it's actually feasible to actually, get to that conditions in terms of, your service.
Yeah, so if I understood your question correctly, you're suggesting there might be a complication that's possibly a hurdle for us because we insist on going to supercritical. So, I mean, let's start off with, with a very basic comment is that it doesn't need to be supercritical to be stored. You can store CO2 as a gas if you want, and you can store it as a supercritical, or you can store it as a liquid. So it's not a requirement. It's just an attractive option because you get so much more in the pore space. And if you, particularly at the high temperature range, there's very little difference in it. It's a very smooth transition from gas to supercritical, and the supercritical densities are not that great at high temperature. So the little example that I showed you here, it doesn't really matter where you are on that on the plot. You start out with a gas and you end up with supercritical fluid, but you hardly notice it because of the high temperatures and pressures. If you inject it into an aquifer, then in a way it's a lot easier because you are already operating at the pressure of the aquifer, and the aquifer is pressure is usually quite high, so you're operating fully usually within the supercritical area. When you're dealing with depleted gas reservoirs, you generally do not. You're starting out with a very low pressure, so it'll be a gas, and then you transition over time as you pressure it up into supercritical. And that does pose a lot of issues with your injection wells. So you've got to manage the transport of CO2, which is usually done in liquid phases or supercritical phase. And then you've got to get that CO2 from the wellhead, where you can control it, into your reservoir, where the pressure is dictated by the reservoir and the permeability and thicknesses of the reservoir, in a way that doesn't cause problems. And so, the issues that you can come up against are massive drops in temperature and unstable flow in your wells. So there's an area I haven't touched on, but it's a whole area of study itself to try and manage the CO2 from surface into the reservoir.
Just a quick one, very quickly to add to that. You have to understand that CO2 injection is not a continuous single phase. It's quite common for the project managers, the operations team, to look at injecting at a high pressure gas phase and then retooling the compressors to a dense phase later on. So you might actually have discrete operational steps whereby you are pressurizing the reservoir up in certain discrete steps so that you're able to reach dense phase, but it's not all the way through all the time. It can be operationally segregated.
I've got a question here from Manushya Takin. Hello, Manushya. It's been a long time since I've seen you, but I'll read your question out. What is the estimate for the total volume of actual CO2 injection for storage in the world, excluding EOR?
Does anyone have an answer for that?
Sorry, say that. 40.
Right, I'll repeat Manushya's question. What is the estimate for the total volume of actual CO2 injection for storage in the world?
Well, yeah, it's about 40 at the moment, 40 million tons per annum, but it includes EOR. I don't know what EOR.
So excluding EOR. So Manushya, 40 million tons a year at the moment. Do you know, I think since you've got that thing around your neck and you're standing up, when someone talks, you could go close to them and then they could, that would increase the volume of what they were saying.
Yes.
Because I don't think you're being heard on that machine because there's not enough actually. But that's okay. Okay, Manushya. Here's another question from, and this is from Adrian Gregory. Great presentation, highlighting the main technical uncertainties. However, the operational issues add further risk. Geomechanical issues with cap rocks, depleted reservoirs have historical well stock, adding significant risks. Speakers' comments, questions? In the UKCS, the feeling is it's more to normal pressured saline aquifers. I think he means by that that there's a feeling that it's more favourable to go for pressured saline aquifers. But anyway, your comments, Shane.
Yeah, so if we just go to the last slide. And yeah, we're comparing the depleted reservoirs and saline aquifers, the advantages and the disadvantages. And let's go straight to the depleted reservoirs side and look at the disadvantages here. Is the legacy wells may leak. I mean, in our experience, legacy wells are the biggest showstoppers in converting depleted gas reservoirs to storage. So that is a problem. Potential problem.
Okay, Adrian, anything else you want to add? Just write anymore. Any other questions that anybody wants to ask?
Yeah.
Can you grab that microphone and keep it a bit, you probably need to press a little button to make it work.
Everybody hear me?
Yeah.
Okay, so here's a quick one. So you show in one of your slides the low salinity, high pressure, we have discussed, and low temperature, they have a huge impact in the solubility. So I noticed in your presentation that the examples that you provided in terms of the aquifer salinity was a salinity higher than 100,000 ppm. So, but how about if we have an aquifer with a extremely low salinity in the order of 500 ppm? So, about how much we will be able to increase the solubility? 2 folds, 3 folds? Any rule of thumb for that?
Yeah, so that's absolutely true. I mean, we prefer low salinities, but we have to go for high salinities. Many areas in the world they've got legislation which prevents you from using low salinity water for CO2. How much difference that makes, I can't actually answer, or I can't give you a rule of thumb. I just don't know if you go from 10 to 100,000 ppm. How big that difference would be. But I mean, I think it would probably be quite could be quite significant, yes.
Thank you.
You're not pressing the button.
I did.
You should be able to hear. Try again.
Okay. All these efficiencies that they were talking about, they're based on the tank models already. So we're not considering like altering the injection or issues with the injectivities. So you mentioned that we're excluding geochemistry, but that can have significant effect if you have like the position around the well, your wells get more injectivity. So all these numbers are kind of rough estimates.
Yes, absolutely. So on the slide where I explained what the material balance calculations do not do, right at the bottom there were a few other points that would need to be taken into account. And so, it's things like drying out of the formation, what effect that could have. I mean, I haven't touched on geomechanics here, but obviously geomechanics is a whole big subject just on its own and can have a major impact on your capacity. That's correct, yeah.
That does prompt a question, which I think on the geomechanics is, in many countries, is there a limit of what percentage of the initial reservoir pressure you can repressure to? Is there any guidelines or indeed any legislation?
I'm not aware of legislation, although they may well be in certain parts of the world. I think that, what we see is that companies wanting to do it undertake geomechanical studies. They get the data, gather the data, and they make they do the calculations to estimate what the safe pressures are, and then they would stick to those. But whether there's legislation anywhere that says you're not allowed to go over 50% above initial pressure, I don't know about that.
I just comment on that. I mean the
Sorry, do use that because otherwise these guys won't hear. Just you have to press the button once and it's on, then it's off. So press for on, press for off.
So it's on which way?
We'll just speak to
When
it.
the green,
Hello?
Speak again.
Hello?
Yes.
Pressures changing may have different effects on the effective stresses around, and also stress gradients. You've got pressure gradients, you've got stress gradients affecting stabilities of fault reactivation or leakage. So yes, probably not just a simple case of we can go up to the what was the previous reservoir pressure or any factual.
yeah, that's helpful. Thank you.
We have another question from our virtual audience. The numbers presented are all speculative prospective resources. How much would actually to net effective storage? And I think there's missing a verb in there somewhere. It just says how much would actually to net effective storage. Petroleum reserves are very different from petroleum resources. CCUS should actually, due to poor economics, be even worse, smaller. Could you make a comment? Sorry, it's not great English, but you get the gist.
Okay, so yeah, so you know, the SPE has brought out the carbon dioxide storage resource management system, the SRMS, and that is intended to parallel the PRMS in terms of reporting of carbon dioxide storage, classification and categorization. And so, you know, instead of reserves, we talk about capacity. Instead of contingent resources, we talk about contingent storage resources. And it has the uncertainty ranges and all that sort of thing in it. I haven't, in any of these, I haven't spoken about how you would classify these things. But in the three depleted gas reservoir examples that we've got, there's one that I would certainly, knowing where the field comes from, I would certainly say that it's a contingent storage resources. It's not prospective. And there's another one which would be classified as capacity. So, you know, some of these are fairly mature projects, and they will go ahead. So the classification follows a similar route to oil and gas.
Yeah. Okay. No more questions I've got virtually. Any questions that anybody wants to raise from the physical audience? Anything else that comes to mind? Yes. Okay. Well, let's part through this thing across. So thanks, Bess.
Thanks very much.
We'll make sure it's on. Otherwise,
thank you. For
yeah.
the call. Yeah. You've mentioned that you haven't looked at injectivity, but you have talked about dynamic simulations. So in that case. And you haven't mentioned permeability. So I'm assuming, based on what you said, that you're only looking at fields that have got particularly good permeability. Otherwise, the injectivity would be limiting this. Is that true? And if not, how are you coping with low permeability?
Yes. So, I mean, when you run the simulator, obviously the permeability comes into it. Permeability is before you select your storage site, you usually go through a screening and ranking and selection process. And, you know, we've done a few studies of company portfolios of assets and helped with the screening, ranking and selection. And permeability is one of the top items that you consider. And if it's too low, you screen it out. So you do want to get high permeability because of the cost of drilling wells and the cost of putting the CO2 away. So it is. I haven't mentioned it once, but it's really important.
Is it on? All right, first time. Yeah, nice to meet you, Hans Izo for BP. So you talked a bit about the dynamic modeling. But I guess we haven't got much of an industry experience to calibrate it with these models, maybe only Schleifler, which has been going for 25 years. What's your take on whether we have the right tools developed to be able to model with any degree of confidence, or are there some things that we haven't captured yet in our modeling?
Yeah,
questions. I guess you're referring to aquifers here more than depleted gas reservoirs. I did have a slide here that I took out, which discussed in any physical system the different ways of estimating quantities in a physical system. And there's the first principles approach. There's a process that relies on data, quantity, and then it's cause and effect. And in the oil industry, we use all three of those: deep time curve analysis, dynamic modeling. At the moment, in the CCS, we'll be right at the top where we're relying on first principles, really, particularly for aquifers. And so a lot of the stuff we're doing is based on interpretation of the physical laws, the physical rules, and putting data into those. And so we're dealing with an awful lot of uncalibrated models. And when we deal with uncalibrated models, the key to success is to do lots and lots of sensitivities and different scenarios. So the point is that we just don't have enough analogs to rely on. I mean, as you point out, slavers, we've got a few others, but we have to use the basic data, and so companies drilling exploration wells in aquifers do need to acquire the data that's necessary to do those evaluations, like cut cores and do laboratory experiments and all the rest of it. But until we've got enough data to start history matching a dynamic model, and we're relying on the theory, we have to recognize there's a lot of uncertainty, and we have to include that in our calculations.
Are there any other questions that anybody would like to pose? Yeah.
This is Brian. This is Brian from CMG. Coming on to that, I think a few words to about the tools. So the CCS work has been going on for Slimer, well over going for decades. So the tools and the technology has been there for a long time. This is just the industry, if you like, going back to what it was doing back in 2000 early 2000. So the tools are there, the simulators, the technology is there, and we're just expanding on what's available. Specifically on that, for example, we talked about the injectivity. Now, Jim, the simulator you mentioned, there's a GIP that's linking the gem to the level of the wellbore modeling tool. So that going to look after all the dynamic phase changes in the wellbore, as well as the technology, if you like, CCS technology that's already in gem. So industry is working on all based on what's available, and there's good amount of work that's going on in the vendor side as well.
Yes, no, I take your point. I think that the tools are developing very quickly, and CMG is one of them. And so it's a question of having the tools, but then having the data to put into those tools. I think, the data is still very much lacking.
Yeah,
absolutely, for sure.
Yeah, going on the forecast, as you said, history match might be pretty well for the production, but going to the forecast, you might have to do a forecast based on multiple realizations rather than a single.
Yeah, absolutely.
Are we all done? Anyone else? Okay. Well, I mean, Shane, thank you very much indeed. That's completely fascinating and so comprehensive. I think we need to be able to work around the records as well. Well, there's food and it's one floor down. I think I should advise you, if you've got valuables, you probably ought to take them with you. I'm not sure whether we can lock this up, but I would suggest that for your own peace of mind. Does anybody here know where the food is? It's the same as last time, and I just want you therefore while I handle things here. Someone.
I think we've got people returning, so we'll just be starting in a moment or two. for those remote.
If it's on,
Do I need that on, do I?
yeah, no, I won't hear you.
You did your
the other
thing,
side.
work it out, but.
Get it working.
Sure they won't hear me through the Jabra.
There you go.
Is that working?
Yeah, that's great.
And this is, you got, you know, this.
Well, that wasn't working.
It's okay for a pointer.
Oh, it was a point. Yeah.
You managed to get it working, but we could.
It's not working.
No, it's not working.
Okay.
Never mind.
Well, thanks for coming back, guys, and I'm sorry online that we're a few minutes late, but okay, we're starting now. And Drew Powell, who I briefly introduced a couple of hours ago, he's going to talk to us on carbon capture and storage, project development, equipment and facilities, aspects and project commercial considerations. The presentation reflects on the current global CCS project slate, reviews the technologies of the carbon capture, transportation and sequestration with reference to current technical readiness and application, and concludes with a discussion of CCS project commerciality aspects. Drew is a chartered chemical engineer and a fellow of the ICME with 30 years of energy industry experience. Background includes business and project management, strategy, commercial evaluation, operations, design disciplines across the energy sector for major oil companies, contractors and consultancies. For the last 15 years, he has worked for Gaffney, Cline and Associates across upstream, downstream and energy transition projects, including several competent persons reports. Over the last 2 years, Drew has extended his role to actively contribute and lead projects focused on hydrogen, CCUS, carbon intensity and carbon management. Drew, the floor is yours.
Tim, thank you. So, yes, thank you for the introduction. It's my details on the screen. As I say, it was when you could leave university with a bachelor's degree meant something, but there we go. Okay, let's talk about, let's get going. I've got a lot to go through and I'm going to move quite quickly because I've got a lot of slides and I'm conscious of the time. So global carbon perspective, let's talk about position, the global position. So it's actually quite positive. I know there's a lot of doom and gloom and people say we're not doing enough, but in the last 5 years, progress has been made in many different areas. I'll put on the screen here some of the progress that has been shown. On the left, there is a typical map that you've seen, no doubt, in numerous other publications, showing the road to net zero, the countries with laws, legislations, regulations related to do with carbon by extrapolation to carbon storage. On the right is those countries that have a form of carbon taxation or energy trading system. So just basically to show you all that things are progressing globally, everything is ticking over. Let's then move on to, I hope you can see that, it's a bit small, I have to admit. So on the left here, this is all 2021. I've sort of taken all the information from an existing slide deck, so there's maybe a year out of date, but it gives you a general flavor of where we are and so forth. We mentioned earlier about 40 gigatons of CO2 per annum being produced. This is from fossil fuels. Actually, there is a lot more greenhouse gases produced if you include agriculture and other industries and so forth. So, but from fossil fuels, we're looking at about 40 gigatons CO2 per year produced. And you can see the split there, China, USA, EU, India, and so forth. As you would expect, those that are relatively industrialized have quite a large proportion of the pie. You see on the right-hand side, a breakdown in just terms of emissions as a percentage of global, in a global perspective. And there's also a list there, and I'm sure that we'll be getting this slide deck. This will be provided to you at a later stage, so I'm not going to go through in detail, but it just summarizes the net zero targets, discussions, commentary of where countries are looking at hitting net zero, as well as their particular approach to carbon management, whether it's through an energy, through an emissions trading scheme or through some form of taxation or something else. Let's move on. And again, just to reiterate, a lot of new activity is occurring, policies, pledges, and so forth from COP26. There was a stronger set of NDCs national determined contributions. A lot of countries have now committed to net zero and so forth. The second column there is showing a little description about progress in terms of carbon pricing, which will come to more detail. Carbon border adjustment mechanism that's been introduced. This is something which is going to play a part in the EU attempting to force other exporters to the EU to look after their carbon emissions as well. China launching an ETS and so forth. So there's a lot of progress going on in the background and in the public eye to the progression of carbon management and the use of carbon pricing and policies and regulations. So we talked about the global perspective. Let's look at the CCUS in particular. Now, there's a bit of discussion earlier today about the emissions. As I said, from fossil fuels, we're looking about there's about 36 billion tons, or billion tons is obviously the same as gigatons of carbon emissions. You can see this is a slightly old slide. It's from the IEA, but it's a good picture. You can see CCUS in there is only the IEA and so forth are only looking at CCUS as contributing 10% of the solution to the reduction of carbon emissions to any form of target that we are setting. Now, this map is showing the blue line there is the sustainable development scenario, which is something which has been replaced recently by the IEA, but it gives a good flavour of what is thought of as a necessity in order to hit the net zero targets. So you can see CCUS of the total is only around about 10%. Notice, the efficiency and also the conversion to renewables that will take the major burden of the transition from fossil fuels in the energy mix into the future. Okay, let's talk about CCUS projects at the moment. Again, this slide slightly altered. It's a little bit out of date, but it gives you again the flavour. You can see that in reality, what we have is in the 2030 timeframe, we're on the way to 2050, the net zero targets in 2050. There is an expectation that in 2030 that we should be utilizing carbon capture for 800. Sometimes you see quotes up to 1,000 million tons per year of total capture in 2030. At the moment, we only have about 45 million tons, I should say, of carbon capture. By 2030, what is currently on the books is round about, in a sort of a, when I say on the books, but in a relatively firm way, because of course there's a lot of rumour and hearsay and projects that are just being talked about without any concrete basis. But in terms of those projects that do have some sort of credibility, we have just under about 200 million tons per year of carbon capture due by the year 2030. As you can see, it's quite a significant gap to where we need to be based on the net zero scenarios, whether it's SDS or one of the others. Okay, so we're not where we need to be, but in terms of what has been announced year on year at the moment, we're looking at 40 to 50% increase every year in projects that have been announced. So even though things have started slowly, the rate of acceleration is quite rapid. So things are looking up, but much more still needs to be done. Okay, I think we've been through this with Shane's presentation, so I'm not going to spend too long on here. Just to add really that there are a number of solutions, including on the right-hand side, we've got coal, as well as depleted fields in the saline aquifers. Basalts as well, the chemical conversion of CO2 is something that's another opportunity. So in terms of storage of CO2, whether it's through deep saline aquifers or oil and gas depleted fields, there is a significant proportion of available storage capacity, well beyond what we need. I think I've seen we'll probably come to this. Well, let me wait until I'll bring the next slide up and then I'll keep on discussing the next point. So I've seen figures, the figures are banded around the media of anywhere between 300 to 800 gigatons of capacity and underground storage of one figure or another. But whatever we're looking at, you know, the point is, since we pre-industrial era to today, we've put about 300 gigatons of carbon dioxide into the atmosphere. So that 300 gigatons could be more than adequately handled if we wanted to extract every single molecule and put into global storage underground through aquifer or depleted fields. What will happen in the short term is obviously depleted fields will take precedent because we have knowledge of those fields, we have models, we understand them, we have existing infrastructure. But into the midterm, saline aquifers are going to take precedent. They will lead the charge in terms of CO2 sequestration. You can see on the right-hand side is a sort of an estimate of the depleted hydrocarbon fields globally. And if you add all of that up, I don't know what it's going to look at, but let's say 300 gigatons. And then on top of that, you've got all the aquifer storage. So the general point here is there's more than enough storage for what is needed if we have the capacity to put that CO2 into that storage. Aquifers obviously are the long term, as I've just mentioned. Short-term depleted fields, obviously the benefits, as Shane has mentioned, we've got all the modeling, the capability, the knowledge, petrophysics, and so forth. So it's a known beast. There are some issues to do with depleted field usage, which we also mentioned earlier. Existing penetrations into the field is one of the major problems that in real life projects is coming to the fore, the need to handle existing penetrations. Saline aquifers analogues are somewhat limited, but as we get more and more technical capability in this area, saline aquifers, because of the volumes available, will become the de facto solution for geological storage. Okay, back to we've got some animation on this. I didn't mean to leave on. Anyway, I think you've seen this before. Shane's CO2 expansion factor. Just to reiterate, I've taken a more maximum view on this, and without going into all the details again with the CO2 expansion factors. In terms of CO2 in depleted fields, we can easily store up to 2.5 times the gas or the oil volume that we have so extracted. So there is, interestingly, and from a technical perspective, it's very interestingly, a greater capacity to store CO2 than the produced natural hydrocarbon that we've already extracted. So the emerging CCUS project pipeline. Let's talk about where we are in terms of pipeline. Now, this slide is slightly older. It's probably a little bit, a few percent out of date. But ultimately, operationally, globally, we've got about 38, 39, 40, whatever, million tons per annum of CO2 capacity. With, at the time this slide was drafted, about 3.5 in construction and the rest in development. So this 166 million tons per annum reflects projects that are operational in construction and in very advanced phases of development. If you look to the sort of the more high level basic definition, those that have been talked about without any real definition, then you're probably looking somewhere towards the region of 700 to 800 million tons per annum. Okay, but you've got to remember, of all these projects, even the ones that are in advanced stages of development, some will falter, some will not continue. So new ones will obviously come to the fore as we go forward. But as with any sort of portfolio of projects, you're not going to see every single one of these. You can see obviously the operational capacity is dominated at the moment from North America, although there is a contribution from other parts of the world. Europe is catching up very much so on some of the planned developments that are going forward. Clearly in Europe, it's very much driven by hubs and clusters. In the US at the moment, it's very much, there's a combination of point to point, plus also hubs. But that sort of relationship, that flexibility, whether we go from a point to point project or to a hub and cluster, is one of the benefits of CO2 because of the flexibility to handle such activities. Again, in another form, these are the types of industries in which CO2 capture projects are actively related to. So you can see there that gas processing is in terms of the operational projects is very much dominating. And on the right hand side, you can see also enhanced oil recovery also dominates at the moment in terms of current projects. As we go forward, what will happen is depleted permanent and depleted fields will obviously come into the fore, and then saline aquifers. And the long-term planning and expectation is that once the depleted fields, which have contributed to the midterm, the long term is really going to be resolved by the use of saline aquifers. Hubs and clusters, as I just mentioned, very strong in Europe and some in North America. I mean, the Far East, Middle East are also talking very much about such projects. A cluster we generally talk about is a concentration of related industries, and a hub is a centralized location where we accumulate CO2 for the ultimate sequestration. I mean, you've probably all seen in the press, you know, we've got HyNet and in the East Coast of the UK, and every sort of couple of weeks there's another hub and cluster development which is mentioned. The clear benefits of hub and clusters over the point to point is very much that the small amounts of CO2 can be collected from a lot of smaller operators, therefore permitting a region or a country to deal with their entire CO2 emissions base instead of having to rely on solutions purely for the large scale. There are commercial synergies, cost efficiencies and so forth, hubs and clusters, and that is the attractiveness and one of the reasons why European governments are very much pushing for them. One of the problems though is because you've got so many players at the same table, that, you know, getting an agreed set of FIDs and the agreement of all parties to go forward with the project can be quite arduous. And I've seen firsthand that's occurring. It has ultimately resolved itself, but because you have so many parties, so many stakeholders, you have to satisfy all of them. And obviously there's complexities not only in stakeholder activities, but also in financial support and financing and so forth. And as Shane alluded to as well, in coordination with the expansion of the CCUS projects and the industry, the regulatory and guideline authorities and so forth are also catching up and supporting SRMS, which Shane mentioned. There's a little picture there on the right, allowing us to systematically report on storage capacities as per PRMS. So again, that's something which is allowed for a standardization of process. But in addition to that, we've also got the ISO standards. 279.4 is the primary one which I know of, which is the site screening, the stage gate screening recommendations for CCUS projects. And in the US, there's also other activities such as carbon safe. And each country obviously has its own approach, but just to say that, you know, the industry behind the CCUS developments is developing and progressing, and the support network there is also developing for the ability for us to take forward CCUS. Okay, let's talk about carbon capture methodology now. So let's get into some of the technology. So very simply, we have a source, we capture the CO2, we process it, we transport it, and it is used or stored. So it's a very simple process. It is subtly different from the classical oil and gas world. It's more of an analog to the LNG world. And as those of you that remember the 60s may recall the complexities and the duration and timescales needed for LNG development. CCUS obviously has to ram all of that development phase into a shorter time frame. Oil and gas, clearly, when we're producing oil, we produce the oil, we deliver it to a delivery point, and then it's a trader or somebody else's responsibility. There's generally a spot market and an open market, very much the same with gas to a certain degree. That's not the same for CCUS. The whole process train requires management from source all the way to sink. So it is an entire holistic project that you have to think about. And when you think about it, that means we have to get FID on every single stage before the project progresses. So moving on to the capture elements, you've probably all seen this as well in some form. We've got the classical pre-combustion, oxy-fuel, post-combustion. So you've got oxy-fuel and post-combustion, basically the same thing, one with air, one with oxygen. burning the fuel, producing the power and the heat, and utilizing methodologies post the thermal utilization to remove the CO2. Pre-combustion is a gasification, an incomplete combustion phase where you produce carbon dioxide along with hydrogen in a reformer, and then you extract out the CO2, leaving you with hydrogen alone as your fuel. So there are all of these technologies which are being developed, and as we talk, I'm sure there's more every 6 months somebody's coming up with a new idea. And of course, there's the CO2 coming out of just straight out of industrial processes such as fertilizer and so forth. So there are many different sources of CO2 and many different ways in which we can extract the CO2 from the process train. Obviously, there's a difference in those production streams of CO2. In some instances, you have high pressure flue gases and CO2-rich gases. Sometimes you have a very low pressure, maybe from an industrial stack or so forth. So you also, within that, you have purity levels, you have high concentrations, such as in ethanol and ammonia plants, some petrochemical plants. And then you can also get very dilute phases. So, as we look at things like industrial furnaces, I just mentioned natural gas turbines, we clearly have very dilute, and you've got to be able to have technology which is able to handle each one of these. And it is no wonder that when we looked at initially the CCUS developments at the moment that are operational, gas processing projects were dominating, because high pressure, high concentration of CO2 is the most cost-effective way of removing CO2. The problem is we have to find ways of extracting CO2 from where costs play a part in a dilute phase. Capture technologies. Again, I'm not going to spend too much time on this, but we have, for all of those like myself with a chemical engineering background, find this very interesting. We've got absorption, membranes, cryogenics, other technologies, a whole range of and a whole raft of different technologies. Dominated at the moment by absorption technologies, the amines and so forth, but all the newer technologies are certainly, they have a place within the process train, but also they have some degree of precedent in terms of these technologies are starting to become more developed and more recognized in terms of technical readiness, and I'll come to that in a second. Very quickly, physical absorption is very simple. The flue gas is put into a column with selective solvent. The solvent removes the CO2 from the rest of the flue gas. The CO2 is then sent for stripping or for reboiling and is removed in a separate separator. It's a traditional type of process, which, it's been around many, many years. I worked on these in my first job in the 90s. Absorption, that's subtly different. The CO2 adheres to a physical surface, and then that physical surface is regenerated using one of several different processes, and the CO2 is therefore removed as part of the regeneration process. Cryogenics, obviously, low temperatures to basically liquefy and separate the components, the CO2 from the process stream. Excuse me. Membranes, relatively new technology, but certainly becoming more recognized over the last sort of 10 years. Simply, you pressurize through a selective membrane, and whatever process stream that you wish to separate, by selecting the correct membrane, you're able to remove. Clearly, CO2 needs to be separated from nitrogen, generally in flue gas. So there's because of the difference in the molecules, you get there's a preference there through a membrane. So, but again, there's different technologies, all which can be tuned into specific requirements of the capture technology. Again, here's some of the names. You've got absorption amines, ionic liquids, and so forth. Physical separation, which is primarily absorption, but one of the complexities, of course, is absorption. This slide's got a typo in it. Absorption is both a chemical and physical type of process, whereas adsorption is just purely physical separation. It's fine, it's detail and probably not something to worry about too much. Next slide. I've highlighted the bottom two issues there, advantages and disadvantages. Just simply absorption, it's been there for many years, it's commercially available, wide application. The only problem probably is there isn't much in the way of cost savings from the learnings, because most of the technology is very mature. So what you get at the moment in terms of CapEx is pretty much it. Disadvantage is it's very highly energy intensive, and as you know, obviously energy is a high OpEx cost, and there's some other advantages and disadvantages, which I'm just I'll let you read those, and you can refer to the slide later when we provide it. However, the technical readiness levels do vary. As I mentioned, absorption is something which has been there for many a year. Membranes, only in the last sort of 10 years that it's really come to the fore as a recognized technology. This is probably a bit subjective. I'm sure you'll have chemical manufacturers moaning at me for sharing this, but this is an expectation that we have of the technical readiness level. It's it's actually a NASA generated system of measuring technical readiness of technologies. And we've sort of put into here where the range over where we think each of these technologies sits. And that was for a project that we did. So again, the point here is that not all of these technologies are as technically advanced and as ready to use fully as maybe others. And the last point from this section really is the challenges needed in terms of retrofitting existing facilities. You can see on the right there a typical production unit. Clearly, we talked about pressure, temperature, and impurities of the CO2 and the impact that will have. But in addition to that, the footprint of these retrofitting an existing development, typically these developments and these process units are not designed for retrofitting. So you have to find the ability to put CO2 removal technology somewhere close by. Land availability becomes an issue, layout, plant integration, because of course you have to build while the existing project is usually live, so you've got hot work and so forth. So there are many, many different aspects which when you retrofit, again, each project is very unique. There's no real standard, but it's something which, you know, is an engineering problem that requires a solution. It isn't just a simple, oh, it can be done. The next point after capture, of course, is CO2 transportation. Most of CO2 transportation on the commercial scale is really by pipeline and ship. We have included rail and road here. I said there was an analog with LNG previously, and this probably still holds in CO2 transportation. The pipeline and shipping for LNG, shipping in particular, has strong merit for long distance transfer. Pipeline has its own benefits as well. You can see on the right there, we've sort of done a very basic cost against capacity type curve, as you would, just for reference really. But all of those do have a place. Even road transportation of CO2. In certain places, there will be small process facilities producing CO2 where the CO2 is not readily accessible through a pipeline system or a railway system or so forth, and so road systems will be required. Again, each project will be bespoke in how you handle it, but there are these technologies available for transportation purposes. Costs, capture, transport, and storage. In a nutshell, capture is the dominant cost. Transportation and storage, you're probably looking at a maximum of sort of $20, $25 a ton for CO2 for any particular project. In the capture facilities, you're usually looking in excess of 60 to 70, meaning that you typically have total capture costs in the area of sort of between 100 and 400 really. Again, each project is very unique and bespoke. It's very difficult to nail things down specifically because there is such a wide range of potential project developments and therefore project costs. But these are sort of very generic, which I think most people have probably seen or know of coming out of places like the IPCC and that sort of thing. So just to give you a flavor that there are lower cost industries and there are higher cost industries, and where you are producing CO2 from these there has to be a recognition that you've got a cost element there. And again, we've talked about CO2 partial pressures does play a part, obviously, on the capture costs. And as I say at the bottom there, of course, you have to throw into the mix your particular position regarding tax credits, investment credits, and so forth. And also your things like loans and credits, where those also play a part on your economics. So economic modelling of a CCUS project is not a simple thing and does require quite detailed analysis. And again, another slide really just to show the range of different carbon solutions and the range of pricing. Again, there you've got your typical MAC curve here, which we've taken. Costs on the y-axis and capture potential on the x. So you can see again, notice how natural gas processing is always in that low cost area, and hence the reason many of the projects at the moment are natural gas processing. And as you go to the right, you get all the way through to direct air capture. And for example, the Occidental project that they're developing in the US at the moment for direct air capture, the only one that's really in a sort of a development phase at the moment. But we'll see how that goes. And if they can bring that technological pricing down to comparative levels with other technologies, then there is a potential market there. Sorry, and the other point really on here is the reason why we have such a wide range in these boxes is because, of course, in different countries there's different approaches. In the US, for example, you've got the 45Q, which drives a more efficient, as in other parts of the world you maybe don't have as many opportunities for cost consolidation, then of course there will be a higher price to pay for certain technologies. Okay, we all know that people are looking around, and we have a project on at the moment looking at in Europe the reuse of oil and gas infrastructure for CCS projects. I think the quick answer is it's a very good idea and it works pretty well. There are some things that need to be considered, and we'll come to that in the next slide. But if you think about it, you've got a platform, you've got wells, you've got pipelines, you've got facilities, you've probably got infrastructure of many different types, all the same things that we would need for CO2 sequestration. Obviously, there's a little bit of adaptation there, but ultimately the vast majority of your facilities are to a certain degree there or thereabouts. In addition to that, where you are producing from existing fields, most of those fields in certain parts of the world where there's oil and gas production, there is also saline aquifer accessibility. So even from existing wells with different completions or redrills, there is accessibility. However, there's obviously a few other issues that go with that. And in terms of the consideration requirements for existing oil and gas reuse, we do have, we've got obviously things like we've got to make sure the size is adequate, but of course that can be retrofitted if necessary. You've got to look at your integrities, your metallurgies, you've got to carry out the analysis. But the analysis generally will be relatively positive. CO2, so to a certain degree, is a relatively benign fluid. It doesn't have as much in the way of metallurgical issues as maybe hydrogen sulfide or other contaminants such as that. Likewise, wellheads, subsea manifolds, platforms, all can be reused. There's a complexity, of course, of taking off existing facilities and putting on CO2 facilities. Typically, CO2 facilities are lighter and simpler than oil and gas, so it should be something that a platform should be more than adequately capable of doing. Umbilical reuse is something very specific and would need to be considered very carefully. And of course, you've got your onshore facilities, which also, very similarly to offshore facilities, can be readily be reused. In addition to that, most oil and gas facilities are in regions where there is a skilled workforce, and the transition of the workforce from oil and gas to carbon dioxide is relatively simple. Skilled workforce certainly helps on your commissioning costs and also your operating costs. Many positives to reuse of oil and gas facilities for CCS. Okay, the next subsection we're going to talk about is we're going to move into the commercial aspects of CCUS now. I'm not going to deep dive here because otherwise we'll get bogged down for hours, but I'm going to give you a few snippets of some of the aspects that we've seen on projects and across the globe. And yeah, and you know, as I say, they're mainly for guidance more than anything. So let's talk about project risk first of all. We've looked at a number of projects looking at risk of the entire process train. As I said earlier, you know, you have to consider a CCUS project holistically. This isn't oil and gas anymore, whereby you know your outlet flange from your separator is somebody else's responsibility. You take your CO2 generally all the way from capture all the way to sequestration, and it's not even then you can walk away, because you have to then post closure monitoring, you have liability, you have responsibility. So there are many different aspects here to oil and gas, and as I say, it's more akin to LNG, but even in that context there are some significant differences. So we've looked at the 5 primary areas, and if you as a company were looking at any of these individually, what would you see as the risks? And we, you know, the perception we have is the capture of CO2 itself is high risk. There's many issues around capture of CO2 in terms of technological, in terms of agreements of the emitters and so forth, liabilities and so forth. So the actual capture of CO2 for the company involved in that part of the process train carries a number of high risk issues, and there's some more bullet points in the next slide to sort of reiterate that. As we move through that process train and we go through to the aggregation, the capture, the delivery and the aggregation, the risks start to mitigate, because these are things which we're used to. They're utility type models. The delivery of a captured fluid and the processing of it and the transportation of it. It's very much what we already do in the gas, in the domestic gas sector. There are also maybe in the refined product sector. We do this already, so our understanding is better known, and therefore the processes and methodologies associated with that carry less risk. So we've assigned some medium risk and low risk to delivery and aggregation. Likewise, the EOR, if EOR or other forms of CO2 usage is considered by the company, then that's pretty low risk. So, you know, we've been doing it. I mean, Shane's been doing EOR since he was about 12, wasn't he? So, you know, it's a well-known aspect of the industry, whereas sequestration then kicks back up again to medium risk in our view. Although we have the capability and the knowledge from subsurface analysis from the oil and gas sector, there are some specifics to do with sequestration that pump the risk back up again. And if we look at capture and sequestration separately and just look at some of the key points there. In terms of capture, the high risk, we're looking at primary risk, economic issues regarding agreements, the ability, the financing of such projects, dependent on local taxation and carbon pricing regimes and so forth. There's also the argument between emitters and between the emitter and the company and the capture, if there's a capture company. You know, take and pay, because what if the emitter doesn't provide the CO2? What if the capture company can't take the CO2? There is a liability for both parties there. Excuse me. And obviously we talked about technology risk, depending on the technology we wish to use. As we get more widespread technologies looking for CO2 extraction, we need to find new methods of getting CO2 extracted from dilute streams and so forth. And the whole issue of liability does come into very much into the CO2 sequestration holistic process train. Likewise, in the actual snapshot of the sequestration, the main issues there regard the regulatory uncertainty at the moment. Regulatory requirements are improving, but historically they've been quite poor. Class 6 wells in the US have taken the best part of 6 years to get approved, which obviously is not in any sensible time scheduling. You know, it just doesn't make it. It's just very poor, and so that type of thing needs to be improved. And I understand the states are taking primacy on that. So it is improving in the US, but unfortunately at the moment, and also in Europe and in the UK, there are elements of regulatory requirements which are slowing down the whole processes. Okay. In addition to that, rights, ownership, that's another key issue that needs to be clarified and understood. UK license round recently was trying to put a definition around that, obviously. So there are many, many aspects which are being worked on, but still introduce forms of risk. Okay, let's talk about carbon pricing, another part of the commerciality matrix. Oh, looks like I've got accidental animation on this. So let me just whiz through this and okay, there we go. So first point is, okay, how do we price carbon? What value does carbon have in the industry? And there are many different ways of putting a carbon price out there. One is a carbon tax, such as in Canada, for example, and the Netherlands is another example. In addition to that, emissions trading systems, ETS, you have the European Union has obviously a very well-known and well-maturing ETS system now, but other parts of the world, China is another part of the world that's looking at an ETS system. Accrediting mechanism, whereby you have voluntary carbon credits and so forth, and you balance what you produce against credits, and in order to balance out your carbon position. Results-based climate finance, and there's more going into investment banking now. And some companies run an internal carbon pricing to utilize in order to rank their own portfolio in terms of economic performance, so that they can identify the most high risk and low risk parts of their portfolio. These aren't mutually exclusive. For instance, in the Netherlands, they do operate the EU Energy ETS system. In addition to that, the Dutch have also got their own carbon tax. So these aren't mutually exclusive. They are just mechanisms that are out there you may come across whereby carbon is valued or it is priced. And move on. So carbon markets and pricing. This shows carbon price versus share of. So this is sort of showing the sort of globally who's running a carbon tax system, who's running an ETS system, where they sit in the actual pricing at the time that this slide was presented, in addition to the relative volumes and the share of the emissions in the jurisdiction. So this is the sort of very heavy slide. The IPC actually have got a figure of for 2030 of between $70 and $100 a ton as being what is required to meet the future emissions requirements. In other words, how expensive does carbon have to be in 2030 in order to drive the mechanisms and the processes in order to reach the targets for net zero? So you can see there's only really a very small 5 to 6% of the entire carbon pricing slate here that actually fits into the IPCC carbon pricing corridor. So at the moment, carbon prices are going up, but they're not high enough yet to drive the processes that the IPCC believe are required in order to hit our targets. Comparisons, again, I'm not going to go into too much detail here, only to say really that there are differences between tax, the trading systems and carbon credits. Carbon tax and ETS are compliance-based systems. In other words, you as an emitter have to meet the compliance requirements, whereas carbon credit is a voluntary system whereby you balance your emissions versus carbon credits in order to overall show in your reports that you are paying for carbon in a certain way. I should also say on the bottom there, emissions level predictability, carbon tax, uncertain because difficult to predict the emissions reductions. Really, ETS, part of an ETS is actually specifying the total emissions, so it's very good at controlling that. And carbon credit is, well, let's leave that open for the time being. There's some more work needs to be done on carbon credit markets. Should be said actually, sorry, while we're here, carbon credits are obviously growing in popularity, and one of the things Article 6 of the Paris Agreement has now been defined, whereby there needs to be a relationship between different parties that are trading carbon credits in order to standardize them. Once standardization occurs and different markets, different credit markets can interact, and they can interact and price carbon at relatively the same level, then the voluntary carbon market should really take off and become a driving force for carbon reduction. So you probably didn't pick that up, but Article 6 of Paris has been one of the successes of the last COP meeting, and we'll certainly be looking forward to supporting the CCS developments. Okay, this slide is a bit heavy again. Basically what it's saying, go to the middle, you'll see that what we're saying is, in terms of the amount of revenue an industry makes versus its carbon intensity, the cement industry makes a lot of CO2 for its revenue levels. But below that, of course, there are others as well: steel, utilities, transport services. These are not out of the woods either. And metals and mining. These are all relatively high in terms of their the amount of emissions they have per revenue stream, and therefore they will see and are likely to experience the highest sensitivity to carbon pricing changes. So you can see on the right-hand side the slide, the part of the slide there, which shows the carbon pricing going up in increments and the impact on their percentage of revenue. So there are many drivers, and the cement industry, you know, to be truthful, is taking steps. There is certainly a movement in many of this in the media, at least, whereby the cement industry is starting to recognize this and is needing to look at developing solutions. The US federal, okay, this slide is, you all probably know about 45Q. It's a tax credit system in the US. It's a federal tax system. It works in cooperation with local state incentives as well, such as in California and so forth. Previously, it was a relatively low, and there was some take-up, but not that much. The Inflation Reduction Act has come in and has changed the ground rules really for 45Q and pushed very much the pricing of carbon up and the benefits. So clearly, what's going to happen here is that this is now going to incentivize a lot of small projects, a lot of smaller players to sequester their carbon and to obtain the credits of it. So relatively recent change from the IRA, the IRA Act in the US, which will have significant impact in accelerating CCS in the US. Sorry. Yeah, Netherlands, I mentioned earlier, is a good example. It's in the EU ETS system, but it also has its own tax rate system. They work cooperatively, the two elements, but the Dutch, in order to manage their emissions, are going to put the prices up into the future. And so the industry knows what's coming and they're able to plan for it. So key conclusions on carbon pricing. It is limited at the moment, but it's growing rapidly. There's a range of, no country globally has the same approach. Everybody looks at it differently, which is does lend itself to the possibility of future standardization at some point. Heavy industry energy consumers are highly exposed to carbon pricing. Only a small amount at the moment of global emissions actually within the pricing bracket for carbon the IPCC suggests that we need, which suggests that increases in carbon pricing and taxation will come at us in the near future. Carbon pricing is very integral to many clients in terms of their pricing. We offer clients these days a sensitivity analysis on the net present values of assets for carbon pricing. Some of them are quite interested in that. And yeah, so okay, I'm going to move on to the next slide now, which we're going to talk about the legal framework and regulations in the CCS space. So 4 elements, really at an overview level. There's emissions policies and targets, legal and regulatory framework, pricing, policy mechanism, accounting and verification. I'm not going to go into detail on this to save time, but you can skip through this as you see fit. The only one I would probably say is an interesting one there under the legal and regulatory framework. The IMO, the London Protocol, also has an Article 6, which has been agreed by a couple of participants to transport CO2 across national boundaries. Up to 2009, it was banned and forbidden. It is now legally acceptable, even though it hasn't been fully ratified on the basis if 2 bilateral parties agree to do it. So the London Protocol has now been modified and amended to allow for CCS transport across boundaries, and hence you've got the things like the Northern Lights project and so forth, whereby you were actually transportation of CO2 across national boundaries. Again, another little slide to show you. I think you've probably seen all this before. Countries with legislation, countries without legislation, those with an NDC from the Paris Agreement. So this obviously is ever increasing, and just to show that much of the developed, industrialized world is starting to take this seriously and is promoting legislation and so forth for CCS. An example. The EU, the EC, whatever, as they've developed a legal framework for CO2 storage. Details there, basically, I'm not going to go into this, but there's a few slides here for the benefit of time you can catch up with later. But just to say, the EU has introduced a legal framework for CO2 storage, which is relevant to all parties within the EU. Key parts of that I've highlighted here in bold. So the characterization of storage, key activities at exploration phase. In the storage phase, routine annual inspections of facilities, monitoring storage. So you see how monitoring and inspection is becoming ever more so important. Closure, when you've got closure, you need to monitor and also look at the surrounding environment. And there's a post-closure, there's also a requirement for reporting. So you don't get away with it. Once you've finished a project, it stays with you, the liability stays with you for a number of years. In terms of those 4 phases of the CCS development, permits and operating obligations, again, I've highlighted in bold what I believe to be the most relevant. Permit rights issued for limited volume area in exploration. I think the Danes are doing it, the UK is doing it very much. Permit rights are being defined at the moment and continue to be so. In the storage phase, exploration, a priority to exploration license holder to go forward with the storage. But obviously things like operator needs to be financially sound. The regulatory authorities are not going to give permits just to anybody. You will have to prove financial stability and also a technical competence, the other highlighted element there. Again, this is possibly going to be a degree of requirement beyond that of the oil and gas sector. Closure, financial security needs to be valid to make sure you're able to pay your liabilities. If there's a problem in the future, you need a post-closure plan, and then once you've got your post-closure plan, you need to action it, and you need to show evidence of storage, conformity to plan, making sure there is no leakage, and you need to make sure there's obviously, as I said earlier, monitoring. But basically, you have a long-term liability, so the project needs to be technically sound. And finally, on this section, obligations and liabilities, storage basically is where I've highlighted. In event of leakage, who takes responsibility, who needs to pay up and look after the field. Competent authority obviously ultimately takes responsibility, but the interested parties in the short term and the mid-term will take liability and responsibility. Right, and that's, I think, the end of my presentation.
What a lot of ground you've covered. Okay, any questions? If you're far away, then yeah, okay. So press the little button, and then the next person lift their hand so that you can move it across.
Can you hear me? Yeah. True, I realized that, of course, being a SPE, your focus was on aquifer and depleted reservoirs. But what are your thoughts about storage in salt caverns for CCS?
I think the problem with salt caverns is very much that it's volume size. You know, salt caverns today are used for really petrochemicals and inorganic chemicals, that sort of thing. The volumes are relatively, conservative in the context of what is currently available. And I think the issue there is the issues and concerns around salt cavern failure and collapse if it gets too big. Saying that, salt caverns, we've certainly looked at salt caverns, and David Garford's there. We worked on a project together looking at salt caverns for natural gas storage in the UK many years back. So I think in terms of it's a possibility of being looked at. I just think the mechanics of it are probably going to make it more costly per unit of volume storage than aquifers or depleted fields, at least in the short term, just solely because of the mechanism required in order to create the salt dome. As you
say, they're being used by a few places for natural gas storage. So natural gas, CO2, what are the differences?
Yeah, I think that the issue with salt caverns is that they absolutely superb for storing and taking out again. So caverns really work best for temporary storage. So you inject very easily, you take them out, take the gas out again. We did a screening ranking study on a whole group of opportunities in which there were caverns, and they rank top of the list for injectability, of course, but they fall short in most other respects. And the big issue is that carbon dioxide is never completely mobilized. You're sitting with a high pressure bubble of CO2, which you want to store for eternity in a cavern, and so there's a long-term risk for that.
Hi, I am from CMG. My question is very basic. So whenever I see those slides and it's beautifully, the technology left and right and everything, but I am still struggling to know who's going to pay for this, right? So my question to you, and probably to the people in here, or lots of quite heavy speeds, right? When is the ownership of the CO2 storage and disposal is going to be on the producer of the CO2? And while I'm saying this, I'm thinking to change my stove into electrical, right? So when is that going to happen? Because technology is there, and we have been talking about CCS for ages, but still it's not going to happen. Like there are tons of feasibility studies, and there is some money there, here and there, credits and tax, etc. But why is not the ownership of the sequestration and disposal, storage, etc., on the producer?
Well, the idea of carbon taxation is to put the onus on the producer. So, you can hear me, can't you?
Actually, you're okay because you're right by this.
Okay, good. So, I mean, the whole idea of carbon pricing and is whatever mechanism that carbon pricing comes in, whether it's a tax or an ETS, it's just subtle ways of ultimately the person who produces the carbon paying for that emission. So yes, the emitter is paying for it, but when it comes to it, the emitter produces it and passes it on in their business model. It has to be passed on, so it gets passed on to the consumer ultimately. So one way or another, whether it's through tax, through grants, through loans, through government awards, you're paying for it.
You should have kept it as it was because it was working. Just talk to it and we'll soon know.
Hello? Yeah, I've got those voices that echoes. Are we trying to inject every ton of CO2 we produce? Or are we saying we're going to tolerate a certain percentage of CO2? Because then there's also the problem of methane emission as well. So here's the question, for the people over there: are you going to inject and get rid of every ton of CO2 you produce every day?
Well, first of all, the numbers that we're talking about, and we've been talking about all evening, are fossil fuel generated emissions. If you look at total emissions of CO2 and you add agriculture and forestry and everything else into it, it's actually a lot more. However, that is part of the natural CO2 cycle, because of course there is a natural removal of CO2 from the atmosphere as well. So I think it comes down to one of those questions that we've added 300 gigatons of carbon dioxide into the atmosphere since pre-industrial in net terms, and obviously we've put in a lot more than that, but in net terms about 300 gigatons, I believe. How much of that needs to be taken out for us to be happy with the position we're in? I don't really know the answer to that one, but clearly a large proportion of what we are producing in the incremental fossil fuel CO2 production does need to be removed out of the equation, and how much more thereafter we need to remove through direct air capture or increased forestry or whatever else, I don't know the answer to that. That one's probably more into the environmental area. I could probably find out the answer, but I don't know off the top of my head.
But you're saying don't forget that trees quite like CO2.
No, I'm also talking about the ocean as well.
No, I understand, but I mean, the trees love CO2, they need CO2, so we can't capture everything. Well, if you can capture, we don't want to, store everything, because we need a certain amount of CO2 for the nature to survive, right?
I want to pick up on your point, just if and I'll speak here because I'll be loud enough. When you went through the liabilities of the operator, those legislation slides, the 2 or 3 slides where you talked about the start of the process right through to the handover, presumably to authorities, and I think it says something ghastly like, and you've got to pay 30 years of operating costs for the operator. I'm thinking to myself, what has the internal rate of return got to be for an operator to take on that big risk? Exactly. I mean, it seems even bigger than for an oil project, because you've got these boundless risks from start to finish, and so therefore the operator needs a high rate of return to make it worth their while. And have you had any discussions with what that rate of return needs to be?
I'd imagine most of that will be covered by corporate insurance. There'll be new insurance mechanisms introduced to allow for that, but I guess the issue is you only pay if there's a problem.
Well, I think my point is simply that you start this project and say, right, I'm going to be a CO2 sequestration operator. After all, that's what we're saying. Whether that's an oil company now or someone else now, they are saying we are now in the business of starting that process from the capture right through to the sign-off. Okay, that is a business model. It looks to me like it's a business model with a lot of risks along the line, and therefore risks normally means high internal rates of return are required to offset the risk.
Yeah.
Any ideas what they might be?
No.
No. I mean,
And you PRT?
15-20% rate of return. What would you go for? I mean, I'm just thinking of because ultimately these projects have to be financed. And that means the operator has to be competent, and then the private equity or whoever's going to invest in that operator needs to get their rate of return sufficient to bear their risks.
But that's not the way to look at it.
Oh, okay.
No, absolutely. The consumer has to pay, because the operator produces, the operator produces fuel, gas, carbon, but then there's the consumer. Whoever the consumer is, the people who generate power, or you and I, we have to carry a risk as well, because we are people who stack rubbish, who produce rubbish. we buy them, and then we take them to, just disposable point.
Yeah.
It's the same thing here.
Yeah.
I'm consuming a lot of energy as a human being, then I ought to be paying tax as well. And that's the way you should look at it. Otherwise, no oil company in the world, I'm talking about RR is not going to come into effect at all. It's got to be tax from the government, tax on the individual, and then some tax percentage from the operator.
I get all that and I understand it. I'm walking at the same time. But I still think that ultimately, if somebody's in the business of being a storage company, they need an internal rate of return for their business model. Whoever funds it, whether it's the consumer, the taxman, the polluter, ultimately you've got a business model and you've got to fund it. And the people who are investing in that business model have to get the rate of return commensurate with that risk. And I think it's a high rate of return, which of course means even more tax and even more.
But sorry, just before you, there's a subtle difference here, right? The step away from the oil and gas world, right?
Yeah.
We're not oil companies that can go out for capital and get weighted average cost of capital finance, right? As a carbon involved party, my entire cash flow into the future is going to be determined by the government, my regulatory authority. If I'm in the UK, government carbon taxation, pricing, and energy and the ETS system will dictate the future pricing. So everything that I have in the future is determined by another single party driven by political whim. Right?
Or market. ETS,
But ETS is dictated by political targets, right?
Okay.
So everything in the carbon world is driven ultimately by political will.
Yeah.
Right? It isn't driven by free market economics. Right? And that's where the real risk lies, is trusting, relying on government finance, basically government financing of these projects.
Go ahead.
You just said it, but just to explain, so in the UK, it's a regulated procurement. Last year, 2 years ago, 2021, there were 2 clusters which were selected by the government. So the East Coast cluster, which is the BP's involved with, and Cline, BNI, with the Scottish cluster as the backup, right? So at the moment they're going through negotiations with the governments. The way it's set up in the UK is basically you've got the separation between transportation and storage companies, East Coast cluster or MEP rather, and HyNet. And the emitters. Government gets to select which emitters are sort of joining the party, but the transportation storage companies are then allowed to charge a tariff to the emitters, which gives them a fixed rate of return. So there's no sort of, and that's being negotiated. I'm not privy to that, luckily, but that's and so the government essentially underwrites that. So the emitters don't turn up, right? It's a risk, as you said. Well, we're still covered. And the government essentially will back up the tariff, right? So I think somebody else asked about that, who's actually paying for this. So indirectly, of course, the taxpayers are paying for this. The government is backing up the tariff that the emitters are paying to the transportation storage companies. But in the UK, at least, back to your initial question, it's a regulated return. And then there's the long-term piece around the liability. Well, that's something, so that's on point. The project finishes, and then you have to demonstrate to the government that you know what CO2 is, and it's you've modeled it, and it stays there, and you hand it back to the government, and you walk away. That's the plan. Thank you.
I would say the entire market is moving away from a commodity-driven free market priced system to a utility model. And so we, as energy firms, we need to be looking at how utility models work and not so much the classical commodity pricing.
I agree with that. I think that's the way forward. Definitely.
It's a utility. Carbon dioxide will be dealt with as a commodity, as with electricity, gas, sewage, broadband, you name it.
Hi, can you hear me?
I can.
Just a point. Your slide showed that China, India, and US are the three biggest emitters. China by far. You talked about the US, but what are China and India doing in this space?
Well, okay, so China is introducing an emissions trading system, and will start to price carbon, but very slowly. As you know, China's net zero targets are 2060, not 2050. I think India is likewise at 60 as well. What's happening in India? Not a lot at the moment. Not that I'm aware of anyway, but at least China is. I think China China always comes over as a country that likes to consider and review and then carry out an activity which is then put into action. So I think the Chinese, once they do get moving on this, it will become a de facto way of life for them. But it's just taken them a bit longer to get going. But yeah, they will be introducing systems. India, I think India will. Yeah, I don't know what's going to happen with India. It may well find itself having to react to carbon border mechanisms. Following the EU, I would imagine China and the US might reciprocate and introduce carbon border mechanisms themselves. And that takes a lot of India's export markets away. So India may well have to, if it doesn't do it directly, it may well have to pay for its inactivity through tariffs.
When you look at how global warming is progressing, almost a straight line. If you look at how global warming is progressing almost in a straight line, you know, these targets 2050, 2060 seem like they are just a little bit too late, really. And I think you've got to get moving much quicker than that.
Yeah, I think it's almost like it's an exponential growth, isn't it, of activity? And I think we're right at the bottom end of that growth, and it's a matter of how fast is that exponential, response going to be. On a positive note, we do have the ability to make net differences, such as the direct air capture. If that can be brought down to relatively, if we can. Most technologies can be halved in price over 10 years. Look at wind, look at solar. Yeah? If we can do that with direct air capture technology, you bring that down to about $150 to $200 a ton. It becomes cost effective in the US at least, and probably in the EU. Once we have direct air capture, then it's just basically net carbon removal. You're not removing any carbon you're producing, you're removing it for other people. And we could have banks and banks of DAC facilities all over. But it's all a matter of drive, isn't it? It's political will and drive, but you do feel that all the major parties are starting to get the teeth into it.
Alexandru, you mentioned about there are different risks for each category or each capture, transportation, offtake. What, in your opinion, what is the better model, the business model, when you spread the risk and all the parties are taking more or less the same risk? Actually, you make an average risk for entire project and spread it to all, or each of the party will take their own risk and will not take any responsibility from the other parties?
I think we have experience as a project in Europe where it's very advanced, and there was a debate between the emitters and the sequestration company regarding liabilities, FID, responsibility. And basically what happened was that both parties, the emitters and the project owner, had to sit down at the same table and sign FID at the same time, because one couldn't sign it before the other because it was too much of a risk. So I think ultimately these projects, as I said, holistically, you've got to think from sink to, source to sink. And for energy firms to think about the holistic train all the way from one end to the other is really unheralded. It's not something that's happened before and now needs to be done. And I think really the answer to it is sitting down negotiating around a table and getting all the parties around a table and saying, let's all agree together to do this. And you know, that would, I think the commercial risk is one of the big issues, and people are not used to that cooperative nature that's needed. But I think it's getting more common and people are starting to talk about it. I think in the utility world, it's more common than maybe in the energy sector. So again, I think there are elements from other parts of industry which may lend itself to promote better negotiation, lower risk, better understanding, commercial understanding for CCS projects. But you know, we're in such an early phase, really. Everything that's gone before has got some sort of unique driver, and what we're now talking about is cookie cutter mass production of CCS projects around the globe. And you know, really there has to be some sort of business model, some sort of, a bit like in LNG, maybe you're looking at some sort of sales purchase agreement similar to the LNG industry. And I think some of my colleagues believe LNG is a good model for the CCS world as well. And there are merits to that.
Hi, DG. I see additional benefits of using existing oil and gas process facilities for CCS by delaying the abandonment and decommissioning liability. But who takes on the responsibility for decommissioning CCS projects?
Yeah, that's a good question, because yeah, durations wise, I would imagine that again, what will happen is there would need to be some sort of inherent agreed position between all parties, possibly involving some sort of insurance policy. But I don't know. I think it's going to be one of those ones that we will have to find out more about in the near future as these projects develop. Again, so many early phases. I mean, most of what we've seen up to now is onshore, right? And what we're talking about is extending this to offshore facilities. And so there's a lot of work that needs to be worked through by competent authorities, current operators, future project owners. Who takes responsibility for what? And I'm sure the only people who are going to win are the lawyers.
Lawyers. Does anybody want to ask a question in the room? I'll give you a couple of minutes, because Luca, are you online? Because I don't have any questions for Drew on my notebook. Is that the same as you, or is my notebook no longer working? I've got 4 questions for Shane, which you've answered, but none for Drew. That seems unlikely. Okay, well, look, Luca's not answering, so I can't do anything.
There's nobody online. It's just because you've locked the door here.
If there's nobody online, I'm sorry. It's a shame you missed it. Okay, well, if there's anybody else, any other questions, or are we done? I think we're done. Thank you very much indeed, Drew. It's really good.
That was good. Oh, Jack. You take it easy. You take it easy. Where are you heading to? Back.
Wow.
That's it. What I was going to say was I probably need to check a few copyrights on a couple of images before I let you have them. It's okay. It's okay.